and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistor, a physics perspective. This is lecture number 52, and the topic of the lecture is design challenges and optimization of CFET for semiconductor scaling. In our previous lecture series, we had looked into the fact about what is a CFET. So, what's a complementary FET? We looked into two types of CFET in the way the CFETs have been arranged. One is basically on monolithic CFET, another is a sequential CFET, and how these monolithic and sequential CFETs vary structurally, that we have seen. Now we come to a point where we will be actually looking into the various design challenges for semiconductor optimization. Now, optimization, when we say, we basically look into design technology co-optimization, which means that can we have a optimized technology and a process flow such that the design initiatives being taken to enhance the electrical characteristics of the device is made better. That we will have a look in that sense. Then we will look into a novel hybrid channel CFET, and then finally look into the synthesis flow for the standard cell library for a CFET. Now, let's look at the few basic challenges, and then we will go to the other sections of the talk. So, one important challenge of designing complementary FET and then realizing it's properly is, the first one is basically the vertical interconnect scaling. So, if you have looked into monolithic and sequential both, the whole idea of CFET is basically stacking. So, you go on stacking active devices one over the other, right? And therefore, the challenge is in reducing the space required for local vertical interconnects. Now, if your stacking height is very large, there will be structural, obviously, instability, but then also the capacitance values also becomes large. So, you need to uh, understand that when you grow an NMOS and PMOS, the pitch between the two layers, if you are doing a nanosheet design, should be so small that this should be stacked very easily one on the top of another. Now, and therefore, that will help in reducing the space required for local vertical interconnect. So, you do not want the local vertical interconnects to go very long or deep inside the system. Otherwise, the interconnect resistances and capacitances will prolong the value of the latency. So, this is one major problem area in a vertical interconnect scaling. Horizontal is not a big deal, but a vertical scaling is a real issue or a challenge in a complementary FET. Now, the second thing is, how do you do a process integration? When I say process integration, I mean to say between NFET and PFET. So, the first problem which comes when you do a sequential design is you need to place the NFET and PFET layer perfectly aligned over each other. If there is a small disalignment between the two, there will be a drop in the functionality of the complementary FET. So, precise alignment between NFET and PFET layers is an important requirement for characterizing the complementary FET. Now, this alignment can be done in multiple number of ways, both physically as well as using characterization tools. But if, say for example, there is some misalignment, the interconnects will not be matching properly between the NFET and PFET layers, and there might be discontinuity in the interconnect layer, which might result in actually a loss of current or a reduction in the current. The second one which people do in a process integration is that they try to put in strain engineering. For example, silicon germanium stacking is done, right. When you do a silicon germanium stacking, that optimizes the performance because the mobility of the charge carriers becomes relatively very large in this case, right. The third problem is in process integration is that you need to manage the defects and the traps properly. Because you see, as I discussed with you in an earlier lecture series, that the fabrication steps are not very easy. So, they are relatively more complicated as compared to a bulk device or a planar device, because first of all you need to ensure that the that the that the steps which we take is precise, and we need to also align the NFET PFET in case of a sequential CFET, and therefore managing the defects and the variability due to complex fabrication step is also a major challenge in a complementary FET. Now, the third concern is the reliability concern for the dielectric wall. What is the dielectric wall? The dielectric wall which separates the N and P layer, right. If you make it too thick, you increase the size of the stack. If you make it very thin, then you have got higher susceptibility to electromigration. There can be BTI, which is bias temperature instability. You can have a HCI, hot carrier injection can take place, and so on and so forth through the dielectric wall. So, the reliability of the dielectric wall is a major concern, or is a major issue, or a major challenge in a CFET. There are many techniques. So people used to have silicon dioxide as the major technique. Now, they have converted from silicon dioxide to silicon nitride, and from silicon nitride to stacked layer of silicon nitride and silicon dioxide in the dielectric wall. There has been also some papers reported where hafnium oxide is used as the separation dielectric wall. Please understand, by inserting such a dielectric wall, you also tend to make the capacitance go high in this case, right. Next point which you should be keeping in mind while discussing the challenge in CFET is how do you deliver the voltage or VDD, power supply. So, power supply delivery is a major challenge, because you need to deliver power to both NFET and PFET, right. And while doing so, if you pass to the active layer of the device, you need to also ensure that you minimize the noise, so that the noise attached to the power supply is very minimum in this case, right. And that is one area where a lot of work is going on in the research field in this domain. Few other issues, and these are not specific to CFET, but nonetheless they make sort of CFET reliability concerns because of this. The first one is basically the self-heating effect, right. Already we have discussed this self-heating many a times when we were discussing FinFETs and other things. But when you look at self-heating effects in CFETs, because of this dielectric wall which separates N and P, there is a very low chance of the heat getting dissipated from the top transistor. So, the top transistor is actually isolated from the bottom and from the substrate by this dielectric wall, right. And therefore, there are large number of heat spots which develop around the top transistor area. This is a major challenge again in CFET in terms of self-heating, right. Techniques are, you might place a heat sink, right, near the top transistor, but then since the top transistor is stack wise at the top of the layer, developing a heat sink very near to the top transistor is a difficult task, right. Then you should also be able to understand there is a problem with the reliability of the device also, right, in terms of aging of the device, electromigration of the device, and so on and so forth. Though you can understand in a CFET, our area reduction has been quite low, or very small area has been utilized, because we are using the same silicon real estate to grow one PMOS and one NMOS over a standard layer, and therefore the costs are small. Another way of doing it is what is known as a dummy finger and smaller islands where you grow these CFETs. Last point is basically in this slide is IO scaling. And what is the meaning of IO scaling is that when you scale down the dimensions of the device and the active area of the device, the IO also starts to shrink, right. The input output also shrinks down, and as it shrinks down, the power density actually increases, and therefore the thermal issues become much more prevalent, right. Moreover, there is a shorter distance between the IO pins, because everything is scaled down. Between the two IO pins, the distance becomes shorter and shorter, and therefore the signals are susceptible to crosstalk, noise, and interference. So, we have learned that IO scaling is a major issue in a CFET, which you possibly won't see too much in a bulk MOSFET or even a FinFET, right? But it's a major issue when you talk about CFETs and CFETs and thermal issues, for example. Thermal issues is also a major issue because there are no paths available for the thermal current or the thermal even the temperature to dissipate anywhere across the CFET value, and that is a rather difficult sort of situation and challenges in case of CFET. Now let's look at the design technology co-optimization challenge, and this is basically a methodology that helps the fab to reduce the cost and the time to market in advanced process development. So there are techniques by which the fab actually tends to reduce the cost, right? And basically TOM, time to market, is very reduced in such cases. If you look at the graph or the figure shown, schematic shown here, then DTCO, which is design technology co-optimization, essentially focuses on the design rule optimization. What it says is, rather than looking at the fabrication steps per se, can we look into the design rule optimization and then capture that optimization in a standard cell logic layout. So let me just underline the point where I am speaking. So first of all, you initially focus on the design rule optimization. Once that has been optimized, then you capture it on a standard cell layout area, and then finally do the full physical design flow. This way your design cycles are optimized and you can actually converge to the best design rule at a much earlier pace as compared to anybody else. Now look at the right hand side figure now, and I have the standard cell library here, SCL. I have this PDK here, which is process design kit, which is available to us. Now the standard cell library is used to synthesize your circuit. This is a standard process flow, physical design flow, which we do irrespective of the type of device which is there, but more so in case of a CFET, that you try to find out the logic design. Within the logic design, you see if the functionality of the chip is maintained or not, do a higher level design, and then do an RTL. Once you have done that, using the PDK, you can look at the physical design part. So the top one is a logic design, and the third one is a physical design. Is physically how the active and passive devices will be placed within the chip area is what will be defined by the physical design, right? And it consists of what? Placement, routing, and then timing. Timing will have what is known as a STA, or a static timing analysis, right? We will have a static timing analysis, and then once the timing converges and as per our regulation, we move to tape out, where the PDKs have been used initially to generate these GDS2 files. But what is co-optimization in this case is that you are co-optimizing the process flow through the design rules, right? Rather than using the design flow itself, right? So this is basically a very basic design technology co-optimization scheme which I am showing it to you. An extension of that is to basically, this is done in order to improve the performance, power efficiency, transistor density, and the cost. And the second part which is useful for a circuit designer is that using DTCO, the standard cell optimization is there, and how you place that CFET for the best available functionality can also be done using DTCO, right? So this DTCO helps you to actually showcase the best of the physical design as well as the logical design. Now if you look at these structures here, this is just a prototyping example which I thought I should share with you, a streamlined technology prototyping example from the netlist for a design technology co-optimization. So we have looked into basic idea of DTCO. We now look into novel hybrid channel CFETs. So the CFETs which we have studied are all standard CFETs, but there are three types of other CFETs which are available, which is known as a multi-screen CFET known as MS CFET, right? We have a multi-bridge CFET, which is MB CFET, and we have a hybrid channel CFET, which is known as HCFET. And they are shown actually on the right hand side. So we have a multi-screen CFET here, we have a multi-bridge here, and we have a hybrid channel here. So we will go step by step and show it to you. Very simple and straightforward, nothing to worry about. If you look at the nanowires in the first case, they are arranged in a vertical fashion and the gate is surrounding in this manner. In the second case, when you do a multi-bridge, so I have got horizontal nanosheet available. So I have a nanowire here NW, and this is my NS nanosheet here, and then they are separated by a certain distance between them. In the third case, where hybrid channel is there, you use both nanowire and nanosheet in order to do it. So I have got 2 nanowires, I can also have a 2 nanosheets available here, right? This can be 2 nanosheets and this can be 2 nanowires. And of course, there will be a dielectric separation between the 2 bodies and so on and so forth. As you can see, so this is my STI, which is the shallow sheet isolation, and as you can see, my substrate silicon increasing as I move from MS CFET to HC CFETs. The dimension goes on, the silicon substrate dimension goes on increasing. Now, typically, when you use multi-configurational CFET, well, where within the same stage you use nanowire as well as nanosheet, typically the wafer orientation is changed to 100 and 110, right? But the device channel direction is always stuck to 110, right? And there are certain reasons for that, which is beyond the scope at this stage. Hardcore fabrication course might be able to sufficiently explain to you why is it like that, right? And primarily, as you can see, the last point, the different orientation of NFET and PFET will help to maintain the mobility and therefore the current of CFET, right? And that is the reason you maintain a certain channel direction within the device itself, right? So what we have learned is that there is a novel hybrid channel technique available, but before we go to that, we have an MS CFET, we have a MB CFET multi-bridge, so multi-bridge CFET, and we have an HC CFET, which gives me the channel CFET. So typically, the layout of any standard cell for CFETs is actually restricted by lateral PN separation. Lateral PN separations means in vertical domain, how much separation is there between P and N. You have to also look into the routing congestion, that how much congestion is there near the active devices, and of course, the performance requirement. So you basically fix up the performance requirement, work your way backwards, check for routing congestions, and then finally look at what minimum amount of lateral PN separation you need to maintain without causing any adverse effect onto the CFET standard cell library, right? Now, there are 2 ways in which optimization techniques are used at very low technology nodes, and these are basically DTCO, which I have already explained to you, and we have a STCO, right? It has come up in a big way nowadays, which is basically system technology co-optimization. The above one was a design technology co-optimization. Now, the DTCO is based on pitch scaling and patterning, and it basically reduces for the 2D integrated series technology, right? Now, STCO is a system technology co-optimization, and it is used in assistance with DTCO scaling, and basically a bridge between a 2D and 3D technology in terms of CFET scaling. Now, CFET standard library cell, the synthesis flow is shown in this diagram at the below, and we typically have the schematic of the cell logic. We know the layouts specification from the cell architecture. These 2 are mixed together to get the CFET cell synthesis, basically the constraints, specifically the timing constraints and so on and so forth. Then you do a placement and routing, and then you check the design rule and the pin accessibility using DCPA, which is basically dynamic complementary pin allocation scheme. This is the middle level of the flow. The lower level of the flow consists of driving routability, cell size, edge based pin separation, M2 metal number 2 track usage, and metal length. And then you finally optimize the cell layout. From there, you can extract the value of the other parameters which are used in the CFET. So, with this, let me recapitulate what we did till now. In our previous slide, we did some amount of basic CFET. What we did was we gave you an idea about, first of all, the basic idea of CFET, right? Then CFET in terms of challenges we looked into, and one of them is self-heating, and so on and so forth. The second one is basically we looked into, uh, apart from challenges, we looked into CFET DTCO, right, which is basically design technology co-optimization, and STCO, which is basically system technology co-optimization, for the best rule check. So you can look into the various design rule checks, design rules, check whether they are functioning properly or not, and we are able to propose methodologies by which you can make the design move faster, more accurate, and better performance. The last part was the full design flow which we get for a CFET. So with this, we will stop at this stage, and when we meet next, we'll start with a new topic. Thank you.